So last class, Aubrey. G. Okay, couldn't remember D. Okay. And you said close enough last time. I'm like, dang it, I didn't get it right, and I hyperventilated on it all night. Worried about it. Okay. So we measured her brain, sort of. What were we seeing? $86 billion neurons, electrical impulses. My poor 8 o'clock student who didn't work yesterday, she came into class, and I sat her down in front of the class, and she was half asleep, plugged her in, we started messing with her brain. When we put her down on the machine, that doesn't sound good. Well, we put her down because she was old. Okay. Her brain immediately started doing this. What does that mean compared to when we put Audrey on there, it was doing that? So which one is more brain activity? The smaller one. So this is a lot of choppy water. Lots of brain activity all over the place. When we put you on there, your brain was very choppy right away. Which means that you're alert and awake, and as soon as you close your eyes, for the first couple times, it took a while to get these brain waves called alpha waves. These alpha waves are a sign of being relaxed. Leslie, I think. Ooh, I could open the scanner and find out. Anyway, the young lady from this morning, as soon as she closed her eyes, all 4 brain channels went. I'm like, you're tired. She goes, yeah, I'm tired. How could I tell if she had been stoned or not? So you can see a difference. You can see a difference. When Arthur was doing it, his brain went like this. It looks exactly like getting drowsy, except more. So when brain waves synchronize, they get larger amplitude. So there's a problem when brain waves synchronize too much. Anybody know what that's called? A seizure. So what happens when you have a seizure is your brain waves synchronize too much. One cell or one little cluster of cells starts sending frequencies, and all of a sudden the whole brain starts following the same pattern. What happens to consciousness when someone has a seizure? No consciousness. My buddy Jake has epilepsy. When he was 2, they were down at Mission Bay. His dad's a professional volleyball player. He's 800 years old now, but whatever. He was back then. And Jake was there. He was running around the beach like a standard 2-year-old, and he fell in the bay. He stepped off the bank and fell in the bay and kind of drowned a little bit. They resuscitated him, and he was fine. But ever since they resuscitated him, he's had seizures. So when he lost oxygen while floating in the bay, he damaged some part of his brain. And then when he has those seizures, they're not like full-on grand mal lying on the floor, completely convulsed. Because the grand mal seizure is where the entire brain becomes completely overwhelmed. And why does a person tense up and shake? Say it louder.
Isn't it that the brain's trying to reset itself?
It's not resetting itself, okay? It's contracting all of your muscles. By activating all of your brain, it's activating all of your muscles. And when you contract all of your muscles, you tense up. And the bodies become rigid and their fists get clenched. Sometimes they'll reach out. I had a student have epilepsy in my class. If you have epilepsy, please let your instructor know. It's not a big deal that you have a seizure in class. If we don't know why you're having a seizure in class, that's major panic. But if you have epilepsy and you have a seizure in class, we're like, all right, fine. William, he never had a seizure in my class, but he had 2 or 3 seizures last semester. He was in one of my classes last semester. And it's kind of funny, but he goes, yeah, I had a bad seizure. And I go, how do you feel? He goes, exhausted. Why would he be so tired after having a seizure?
Because your body's so tense and it's not flowing oxygen around the
And it's not just oxygen, but you're also activating your entire brain. You felt how tired it was trying to move the damn cube. And it was so funny because the young lady this morning, her hands were all sweaty too. Because at that same kind of, you're trying so hard, you're burning a lot of calories by activating all those brain. And so William was trying to take different medications to stop the seizures, but what happens when you take medications to stop brain activity?
It takes down the rest of your brain activity.
It takes, you don't have much brain activity. So he'll be sitting in class kind of just staring, one eye just goes like this. Off to the side. Like, dude, you changed meds. He's like, I don't even know. Just stop. Okay, but, so, the thing about this about the brain is that it's all just a series of electrical impulses. Why do we have this brain? What's the whole point of it? Why release all these transmitters? I think we talked about most of these, right? Yeah. Why have them? Sorry, that was on. I gotta make a mark on my monitor where that is. Okay, it's right on the little blue clip. Why do we have neurotransmitters? Why do we have electrical activity? Thank you. Okay, movement. It's so you can move. Why do we think? We're structuralists now. This functional psychology is a pile of crap. We're structuralists. Oh, I said functionalists. Okay. By being a structuralist, the reason we have a brain is to produce behavior. If we understand the structure of the brain, we can understand why you behave in a certain way. Why is that not true in the real world, only true right now? Why do you behave the way you do?
There's different factors in the world.
Yeah. There's a million, she said there's a million factors in the world on why we move and why we choose behaviors. Two people giving exactly the same choices, given exactly the same situation, could they make different choices?
Yes.
And have reasons for making different choices? Yes. Yeah, like yesterday during the thunderstorm, I wanted to go outside. Yay! Weather! I love weather. It was exciting. Right when my class let out yesterday, so all the students walk outside. It rains once a year, and it's right when I need to walk to my car. Sorry. Yeah. Okay, but so for me, I wanted to go outside to watch the lightning. It was boring lightning, by the way, just short little flashes. Not much energy in the storm. When you get a really good storm with a nice Santa Ana and the tropical hits it, anybody seen the really big, long lightning you get?
Oh, yeah.
So beautiful. Across the sky. I sat up on the top by Granite Hills High School once, overlooking the El Cajon Valley, and watched a big storm roll across. It was so awesome. I was trying to video lightning on my phone. Finally, I got soaked. I'm like, okay, I gotta go inside. Okay. So, did we talk about this part of the brain? Oops, sorry.
Yes.
Yes, I wrote it in sparkly rainbow for my other class because what does this part of the brain do? It tells you to stop. This part of your brain is called the amygdala. I always say you're your annoying friend Amy because it's always telling you to watch out, be careful, look at that, pay attention to this. Whenever you're afraid of something, your amygdala's ready to roll. Okay, so what I have some cool pictures for you. Okay, let me make this smaller so it fits on the screen. Okay, so this is a brain. Okay, so when we look at this brain, what do you see? It's supposed to do something. There it goes. Come on, slow computer. What does this do? What is this? Sorry, what does this do? Okay, when I look at, what do you see when you look at this? You see something. I see a butterfly. What do you see? Don't say brain. It's a brain. Different colors. Okay, this is black and white. But the different colors you see are gray. I really want to try to do this, but it doesn't work that way. So the gray matter are the neurons. The gray matter are the neurons. The white matter is this chemical called myelin. This chemical called myelin is insulation. You ready for this? This is very tricky. In the gray matter are all my neurotransmitters. In the gray matter are all the neurotransmitters are. So what's on the white matter in the myelin? The axons. But what have we been talking about that's in there? Synapses are actually in the gray matter. Because synapses are where the vesicles are, where the neurotransmitters are. So what's in the white? What's happening in the white? I'll give you a hint. Electrical activity. The electrical activity of your brain is in the myelin, in the white matter. Myelin is fat. If you take a chunk of meat and cut it in half, the white part is fat. So our brain is very well marbled. I'm sure it's very tender. Yes. Okay. Whenever we buy, we don't eat meat, red meat that often, but whenever we do, we always buy very lean meat. We don't eat a lot of fat. And so like we go get a piece of meat, we're like a London broil or a nice non-fatty piece of meat. People, don't you want like a ribeye or something? I'm like, no, it's got a lot of fat in it. They're like, but it tastes good. Well, it tastes like fat. I mean, which it does taste good, don't get me wrong, but meat also, well, meat's not good for the world, so we eat it anyway. It's an easy source of protein. So when you look at this fat inside the brain, do you notice that if I can start here, at this neuron, could I get with the electrical activity to almost anywhere in the brain? Every cell in the brain can be connected to every other cell in the brain through this giant myelinated highway. Through these axons. The axons, remember that picture from the Connectome video? Did I show you the video with the guy with the slices of the brain? Everything's connected to everything else. That's happening in the gray area. In the white, the axons are sending information to other gray areas to interconnect and connect. And connect. Wow. Okay, so what else do you notice about this? Where are most of the neurons? On the outside of your brain. So the outside of your brain, it's actually kind of funny, starts all the way inside here and goes all the way around the outside. So we were just in my last class, we were actually making brains out of clay for my physio course. They have to remember 60-something parts. You have to remember like 12. So we're making clay, and my hands are green because the clay evidently stains your hands. Who knew? Okay. I got a really nice green thumbnail because I was using it as a tool. But, so if I wanted to make the surface of the brain, I flatten out a piece of clay really, really, really thin. And then I fold it up. Why do you think our brain is all folded up like this? You have the knowing smile. Why is the brain all folded up? Well, it's interesting. It's all connected through the inside of the folds. So if you were to spread this, if you were to spread a human brain out on a table, unfold the cortex, it would be about 1 meter by 1 meter. That's a big ass head, and really thin, so the wind would really catch it back. So, but why wad it up in a little ball? So I can actually fit a lot of cortex, a lot of brain, in a very small area if I fold it up. And the way, when I was in graduate school, I worked with children with fetal alcohol syndrome. And sadly, a lot of kids with fetal alcohol syndrome, their brain doesn't have wrinkles and folds in it. In fact, I can actually give a good model of this. I don't want to use Internet Explorer because I'll get a virus. Go back here. Here's a picture of a manatee brain. Well, you can see it down here. How many folds does it have in it? 2. 1 on each side. There's a motorboat. Ow! Hey, cabbage. Anybody used to go watch the manatees at SeaWorld? They've left, and I'm very sad. I don't really like SeaWorld so much, but these guys are so cool. Look at them. They're called sea cows. I follow a manatee thing on Instagram, and there's a dock where there's a water spout, and the manatee just comes over and goes at the water spout. Do you think there's a lot going on in there? No. There's some that live in the rivers in China too, and they're exactly the same. What's their number one cause of death? Motorboats. Because they don't swim very fast. They don't notice when a motorboat's coming. Yeah. It'd be a nice life though, wouldn't it? Do I really want to look at the 12 surprising facts? No, I don't. Okay, moving on. Okay, so we're different than a manatee. At least most of us. I do love lying on my back eating cabbage, but that's not important. Okay? But, so the kids with fetal alcohol syndromes, their brains looked like those manatees. Smooth in certain areas. Because prenatal alcohol exposure slows neural growth. And if the parent drinks a lot during early childhood or during early development, the brain just doesn't grow. Anybody seen the Zika virus stuff? It's really horrible. If you're feeling really good about yourself, you got a good batch of self-esteem going, just Google. These babies are born with little tiny heads. It's called microencephaly. And they're very strong emotions, but they don't have much ability to learn. Because what's missing? The surface of their brain. Their brain just doesn't grow past the middle parts, which we're going to talk about in a little bit. Really sad. Okay, so am I going to expect you to know everything about the brain? Why not? It's too much for you to try to understand an introduction to psych. So I want you to keep the idea that the way we're going to be talking about this is that I want you to focus on the main reason we're taking a psychology class. What's the whole point of this class? Checkbox. No. So your job is to try to understand people's perspective. Remember the first day of class? Understand why people see the world from different perspectives. So by digging into the brain, we're going to show you how brains work. Every single one of your brain works the same way. But every single one of your brains is different. Our brain works the same way as a mouse brain. But our brains are different. We're special because we have baggage. Okay. Isn't it pretty? Do you want to start bottom up or top down? What do you think? Top down? We can do top down. Top down works fine. Okay. What is the most human part of the human brain? What makes you special compared to anybody else? Oh, I think cats, dogs have emotions. That doesn't make you any special. Makes a lot of people so annoying too, actually, but it's important. Okay. What makes us special?
We have cognitive abilities.
Prove it.
Just speaking is
Yeah, we can talk,
But
make decisions.
has anybody ever had a general anesthetic?
Yes.
Okay, so people who have never had a general anesthetic, you can have a full-on conversation. Are you even aware that you're talking or hitting on the nurses or whatever? Nope. Okay, my brother was in a bad car accident a long time ago. It's actually in a bicycling accident. Got hit by a car. He was like grabbing nurses and talking to people and having it. Where was he during this episode? Unconscious. They'd give him an anesthetic. He had no consciousness whatsoever. But why was he still acting, behaving? Because parts of his brain were still working. Somebody's battery's about to die. I can hear it. Oh, was that a phone call? Okay, sorry. Why do you have the battery warning sound as a phone call? It's weird. Okay. Sorry. Squirrel. Okay. So now, but what makes you conscious? Don't say your thoughts. This is really complicated, isn't it? You think, oh, I can easily, I don't know. I don't even know what's real anymore, man. Okay. I'm going to write this up here. Is that the first thing that came to your head? Yeah. So, you have the ability to think in the future. You can think of what's happening after class. You can think about what's happening next. Most organisms can't do that. There's only a few organisms on our planet, a few upper primates and some crows, that can actually think into the future. That actually think into the future. You can plan. This part of the brain right up here, this prefrontal cortex, it's right behind your eyes. It's actually called the orbital prefrontal cortex. So when I ask start at the top down or for the bottom up, that's the most important, most sophisticated part of the human brain. That's the most complicated thing that we have. It's called the prefrontal cortex. If you are depressed, depression has a million behaviors associated with it, but it comes from the left prefrontal cortex, right here. Anybody know how they used to cure depression? Lobotomies. So we cut out that part of the brain, and what happens? You're not depressed anymore, but you're also not yourself anymore either. That part, by cutting out that part of your brain, you lose motivation. By cutting out that part of the brain, you lose the ability to plan in the future. You lose the ability to do anything. So yes, you might be depressed, but you're not going to commit suicide. What do? You just sit there and smile. You become a lapdog. Okay? It's kind of scary. So the prefrontal cortex is all about planning. When does your prefrontal cortex finish growing? 25, 26 years old. Your brain continues to grow prefrontal cortex up and through your mid-20s. So this is one of the reasons why we have a bunch of high school kids who want to take college classes. And my adage is, dude, goof off in high school. Because your brains are still growing. There's so many spitwads that you can throw at people and you do it in college, people are like, moron, you do it in high school, it's funny. But when we have high school kids taking college classes, sometimes they understand all the material, but do they get the big picture? No. Some young people, what we call old souls, they develop prefrontal cortex sooner. When these old souls, they develop prefrontal cortex sooner, they're able to see bigger picture things. When I taught this very same class to high school kids at Ramona High School years ago, they did not get it. I've had the same student take my Introduction to Psych course at Ramona High School, and then they took it here a couple years later when they got out of high school and they came to college. And they're like, the class is almost the same, except they understood it so much better later because they have the ability to think about themselves in the now, in the past, and into the future. But I've had a couple students that are 14 taking my class, and they did better than some of the 22-year-olds taking my class. Because everybody's prefrontal cortex grows in a different way. So in order to understand how this prefrontal cortex plans, we have to fill in the rest of the brain to try to understand it. So give me some other behaviors. What else? What helps you plan?
Your emotion.
Okay, so emotions are inside the brain. Those are actually, animals have the same emotions that we do. Humans, horses, and dogs have all evolved together. There's very few wild horses. All the horses that are in the United States are leftovers from the Spaniards' horses. There may be one or two generations not domesticated horses. So if you go out into Montana and snag a horse off the prairie, you can bring it home, and will it be your friend and a pet? That you can. It's only one or two generations removed. There's some ones that are like badass horses. They're really hard to train. But most of them will accept humans as a part of their own self. Same thing with most dogs. You can domesticate a dog that you find wild. You cannot domesticate a coyote. Because coyotes are wild animals. Most dogs are descendants from other dogs that we have bred out of being wild animals. Take epigenetic stuff. It's really neat stuff. Anyway, so what's something that is unique about humans? What can we do to make choices, to make plan? I'm going to write the word choice up here because that's something that's really important.
We can organize.
But organization is a method of planning. What do we use? So how do you know what you're going to do right after class? Let's put it that way. Pain? Oh, hunger. Yeah, I'm hungry, but I ate my eggs on the way up here, so I didn't have to eat them in front of you because you freak out when I just put the whole thing in my mouth, so I stopped doing that. It's a waste of time to take bites. Just put the whole thing in your mouth and figure it out later. No, you chew burritos. Don't talk bad about burritos. Okay. Okay. I'm fighting words. Okay. Okay, so we have to rephrase this question. Okay? So I'm going to draw a couple lines on this brain right here. Okay? These lines represent what we call fissures. So what these lines represent are kind of sections of the brain that are different from each other. These are called lobes. These are called lobes. In order for you to make a choice and a plan, you guys the people that have chimed in, keep going for things that are unconscious, like your emotions, being hungry or thirsty or pain. Those are deep. Animals have all of those. What are the conscious experiences of trying to make a choice? So you have to choose what kind of burrito to get. Thank you for throwing a burrito into my consciousness. How do you decide what burrito to get? Dos burritos, the best kind. Oh, sorry. Okay, so your memory is located on this lobe right here. That's terrible contrast. Oh, it works up there, though. It's in the temporal lobe. Your memories are located in the temporal lobe. There's a part of your temporal lobe. There's a part of your temporal lobe where you hear sound. Okay, this is really kind of creepy. Let me draw this here. This part right here, I'm supposed to change color, stupid pen. Okay. This part where I'm drawing in black, this is what we call your auditory cortex. Has anybody in here ever had something called tinnitus or tinnitus? What is it?
The ringing sound in your ears.
It's not in your ear, it's in your brain. Yeah, have you had it?
To an extent.
Yeah, so what was yours caused by?
I was riding horses and my horse did a 180 because it got scared of something and I slid right off and smacked my head on the rail.
Helmet?
Yes.
Thank you. Okay, so you were going to get a scolding. I had a student named Bree who fell off a horse and it smashed her parietal lobe. It smashed her brain right up here. And she lost the ability to feel a large portion of her left side. Yeah, because it smashed here. She lost a large portion of her left side. Because what did she smash? The brain where you feel. Her arm and her back and her nerves were perfectly fine, but where she feels up here was gone. So if you hit your head, sometimes you get what's called a temporal lobe concussion. It's called getting your bell rung. It's a term they used to play in football, and they used to say, shake it off, you just got your bell rung. Now we say, please sit down, please don't sue us for having a traumatic brain injury. But whatever. Back in the old days, it was just get back in the game, don't worry about it. Okay, but when you get hit on the side of the head, your brain sloshes to the side, and on the temporal lobes, on the side of your head right here, that's where you hear sounds. So if I were to flip the machine around and send electrical current to your brain, we can't do that, but if we could, I could zap here, and what would she experience? Boo, boo, sound. The cool thing is each little cell along here again, take physio if you really like this stuff. Here's a certain frequency. Every cell along here hears a certain frequency. So if I activate this one, it's boop. If I hit this one, boop. And it goes right up that pentatonic scale. So everybody hears the same notes. Everybody hears the same basic notes. It's really cool. What if you have nerve deafness in your ear? What happens? You don't hear certain notes and certain frequencies. It's really kind of neat. A good friend of ours, was a kid, a neighbor friend kid named Oliver, is missing a part of his ear nerves. They just weren't born without them. So he has this thing glued on his head. A student, William, last semester has also a thing glued on his head. The hearing aid goes directly into his brain and has a speaker on his head. What does the speaker do? A microphone, technically. It's like this thing. Not that big, though. That'd be cool. What does it do? His ear nerves don't work, so it puts the frequency directly into his brain. Can he hear normally? Could she learn to move the cube? Kind of. So he learned, because he put a little more time and effort into it than you did. You're half-assed it. But if it was really important, you could spend hours doing this, and she could easily move the cube left and right, no problem, because the machine and the brain would interface with each other. And that's what he has with his ocular implants, is he's learned to hear the sounds that it produces. I'll play a video of that shortly, which is even weirder. Okay, moving on. So the temporal lobe is where you hear and remember. Okay, this is also really kind of strange. This is where language is. Language is in the same temporal lobe. Language is lots of different things, though. Language is located in different parts of the brain. But when you hear something, most people use words for language. When you're reading, do you hear the words? Anybody who's an English language learner can hear two different languages when they... So someone's speaking to you in Spanish, and then you're thinking in Spanish, then someone asks you a question in English, and you go, okay, and then you can go. A lot of people Spanglish, where you find the word that's fastest to find and just let it roll. My good friend speaks Farsi. Her name is Sherry. It's so funny because she's talking to her mom on the phone. She can't talk to her mom in English because her mom speaks English fine. She speaks English fine. But why does she have to talk to her mom in, bless you, in Farsi? Because she thinks with her mom in Farsi. Wait, so your language, you have two languages here? Yeah. Each of the sounds map to a different part of your consciousness, of your memory, to map a different language onto it. My son's learning Spanish right now. It's really entertaining for him because he's rattling off all the Spanish words, and eventually I'm stupido. Anyway. Or something not intelligent. I forget what he was doing. Anyway, but it's funny because as he's trying to learn the words, he's trying to say the sounds that he's hearing and going on. And I can't speak Spanish to save my life, but I've been around enough people that are speaking Spanish. I kind of know what people are talking about. I know some of the words. And I can pick up, can I use the language or can I communicate? Is communication the same as language? Because there's a lot of language that occurs here. Why would I have language occurring in the prefrontal cortex as well as the temporal lobe?
To know what you're going to say next.
To understand what you're going to say when you say it. So this is why we teach students who are English language learners to practice studying in the language that they're being tested in. I have a bunch of students last semester that spoke Arabic, and they were really struggling with my class because they'd go home and study in Arabic, and then come to class and learn in English, then go home and study in Arabic. they have to study twice as much to gain the same information. Because they have to train their brain in twice. They have to memorize everything twice. So even though it's really struggled for them to learn English, if they study in English, what happens to their English ability? It grows, but it grows in the way that they're being tested. So you actually, it's like, I need to run a marathon, so I'm going to go for a bike ride. It's both exercise. It'll work, right? No, I might be cardiovascularly fit, but running is a lot different than biking. So if you've ever done a triathlon, there's a thing called the transition period, where you get off the bike and you have to start running. Your muscles are like, what the hell are you doing? It's awful. Awful. Never run at all, ever. No, I'm kidding. Okay. I hate running. I love running, but I can't do it, so I hate it. Okay, moving on. So, this lobe up here, it's called the parietal lobe. Let me change colors on that. At the top, it's called the parietal lobe. The parietal lobe is where you feel. This is where you feel, not emotion feel, physically feel. Not pain receptors are actually down here, lower part of the brain. It didn't drop it. Down here. Pain's down here. But this is where you know where it hurts. So if I were to flip the electrode circuits around and stick the electrodes into your brain and I zap somewhere along here, you would say, oh, I felt something on my cheek. Oh, I felt something on my hand. Hey, that's my leg. Ooh, don't do that. You can actually find your entire map of your body right here. All the sensory nerves are here. There's a really horrible thing called if you get deaffernated or lose a limb, okay, what happens to that part of the brain? It still works. So I had a student, Colleen, in my class. Very cool student. She had melanoma, and so she had her arm amputated at her right above her elbow. And her hand would hurt. It's in a medical incinerator somewhere, in Encino County. So how is her hand hurt?
Still there.
The brain still feels her hand. But what's interesting about this is the way that you feel, it's the same way that you can't feel that cube moving, but how did you know the cube was moving? You could see it, which is right here. And this is, I'm going to put this up here. What you see, you're going to start to see that everything is connected to everything. And this is called the occipital lobe. The occipital lobe is where you see. So where you see is right next to what you feel. One of the things, if you ever crash on your bicycle and they say, oh, don't look at it. Because what happens when you look at it? It hurts more. Yeah, just don't look. Just don't look. Just walk away from that. Because the occipital lobe is directly connected. In fact, there's not much gap between the parietal and occipital lobe. They kind of all blend together. And so what you feel is a lot of what you see. You're going to start understanding a word called feedback. Feedback. Feedback means that sensory information comes in, behavior goes out. Sensory information goes in, behavior goes out. That's feedback. So our occipital lobe is one of the biggest parts of our brain. Humans see extremely well. Why is wearing glasses so important for us? But why, so what? The better you can see, the faster the rest of your brain works. Anybody ever had to try to do like plumbing, like under a sink and up, trying to fix something or reach something that you can't see? Computer work is awful like that, trying to plug a cable in from behind the stupid damn computer. So frustrating. And the reason it's frustrating because if you can't see it, you have to run just on feel alone, your prefrontal cortex has a really hard time figuring out what to do. Prefrontal cortex has a really hard time figuring out what to do. So now, Is this overwhelming or easy so far? Easy-ish. For people who like brain stuff, you go, yeah, more. But for people who are like, don't want brain stuff, like, I don't care how the brain works. You're talking about burritos. I'm hungry. Okay? So we're going to get to the stuff that's a little bit more interesting, because this is just boring old consciousness right here. Just consciousness. You see something, your occipital lobe lights up, starts sending frequencies. The frequencies go to your memory. What do they tell you? Okay, so I'm going to play this little video clip for you. I should have Windows open somewhere. I guess I don't. This is one of my favorite videos of all time for TED.
Well, I was born with a rare visual condition called achromatopsia, which is total color blindness. So I've never seen color, and I don't know what color looks like, because I come from a grayscale world. To me, the sky is always gray, flowers are always gray, and television is still in black and white. But since the age of 21, instead of seeing color, I can hear color. In 2003, I started a project with computer scientist Adam van Don, and the result for the collaboration with Peter from Slovenia and Matthias Mizano from Barcelona is this electronic eye. It's a color sensor that detects the color frequency in front of me and sends this frequency to a chip installed at the back of my head, and I hear the color in front of me through the bone, through bone conduction. So for example, if I have like, this is the sound of purple. For example, this is the sound of grass. This is red. This is the sound of dirty soft, which is like yellow, this one. So I've been hearing color all the time for 8 years, since 2004.
So listen carefully.
I'm completely normal now to hear color all the time. At the start, though, I had to memorize the names you give for each color. So
I had to start by memorizing the names you people give for each color. Does he understand what color is? Never ever seen it. His eyes do not produce the pigment, so he cannot see color. Black and white only. However, does the world exist in color? We see it in color. Does anybody have any color blindness in them? Nobody? So there's red-green colorblind is the most common. Blue-yellow is second. So some people are red-green colorblind. So when they look at this color, what do they see? Red or green? It's the same in their brain. They don't see red or green. They see a color which is red or green. So like if I draw on the board with an orange marker, they see a light gray on a white background because of the red's missing. And all that's left is a little bit of yellow on the back. Anyway, so he had to memorize the notes. Boop, red, boop, red, boop, red. Got it. This is what the brain scanner was doing with her brain. Brain-machine interface. She figures out, oh, I do this, it moves. As soon as the girl this morning, I did not tell how the mouse worked. I say, just drive the mouse around. And she like turned her head, the mouse moved, and her brain goes, got it, turn the head, mouse moves. She was able to fly around. She only got like 78 on Slither. But she was able to actually play the game. I never gave her any instructions on how to do it. How'd she figure out how to click? I set it to teeth clench, made her to clench her teeth, and she just happened to clench her teeth when she was trying, and it worked. So the feedback. First, you have to do the work, memorize, then listen carefully.
I had to memorize the notes, but at the same time, all this information became a perception. I didn't have to think about the notes. And at the same time, this perception became a feeling. I started to have favorite colors, and I started to dream in colors.
So what did he learn? Hear color. Okay, so let's go back to the brain here. So color happens to be right here. That's where you see color. Is it occipital lobe or temporal lobe? Temporal lobe. Temporal lobe. You see colors in the temporal lobe. Yeah, all the light comes in, it goes to the occipital lobe. This is where you see, but then here tells you what color it is. So wait, what's located right next to the color areas? His auditory cortex. It's not a very big stretch between the two. If you learn to read a language, does that mean you can speak it? No. Learning to read a language is the occipital lobe over to here. Learning to speak, you can learn to speak it without being able to read it. A lot of humans learn to speak and have good fluent conversations without the ability to read. Because that's a different pathway to getting into language. You see how just one little kind of thing starts becoming more and more complex? That's the cool thing about our brain. It becomes more and more complex. So, do you have a self? I don't have rainbow sparkly on this one, but I do have this pale orange. Here's your self. It's like skin colored. Not quite. Okay. Very bad fake tan skin color? Okay. There's your self. What happens if I cut that out or anesthetize that? You have no perception of who you are. It's actually called dissociation. Some people get under very stressful situations and all of a sudden it feels like you're standing beside yourself during that really stressful situation. General anesthetic, a lot of times people dissociate themselves. You're lying there on the table, all of a sudden you're floating above yourself on the table looking down. Wait, hey, oh geez, I'm dying. At least I'm going up. Whew. Okay. I didn't find out about that. Good. Okay, so, but the idea is that this is where your self is. Where do you reach and connect with other people? Where are other perspectives, other selves? Right next to yourself. There's a really cool thing is that my wife and I have been married for almost 21 years this summer. So we had our 20-year anniversary last summer. And do we know each other pretty well at this point? Yeah, she still says, I can't believe you just said that, because I say what I'm thinking and sometimes I should shut up, but whatever. But ourselves have merged together a lot because we spend so much time with each other. We're the kind of people that when we have free time, we want to spend with each other. We have some friends that actually, weirdly, are no longer married, but whenever they had free time, they wanted to go do their things because they had to spend so much time together, they wanted time alone. What does that bode for in a relationship? Not good. Not good. That means that you'd rather spend time apart to enjoy yourself. Just saying. Okay, so the interesting part, though, is that when she is hurting, do I feel it? I didn't have the sympathy labor pains, but some husbands get that. Wife's having all contractions of uterus. I didn't even got a freaking uterus. All of a sudden my stomach hurts. Why would my stomach hurt? She's feeling the pain in my parietal lobe. I'm seeing her feel the pain, so all of a sudden myself goes, you're feeling it too. Are they real symptoms? Yes, they're real symptoms because you're actually feeling it in your brain. Does Colleen really feel her hand? Yes, because it's her hand that she's feeling. It's real to her. She actually got what's called a deep brain stimulator. The deep brain stimulator is 2 wires that go in the middle of her back where her arm nerves go in. And whenever she is feeling that pain from her hand, there's a switch, or there's a little thing that she can do, like I think it's a little magnetic switch, that the switch is under her scapula back here. She can put the little electric thing on it, and it feels like someone's dipping her hand in warm water. The missing one. So it activates the nerve, the feedback circuit. So why would your hand hurt? But if it's gone, it shouldn't hurt.
Because you're trying to contract the muscle.
You're trying to move it, but it won't move. And so it feels like it's constantly clenching and aching because you're trying to move it and it won't move, so it feels like it's stuck. So by sending that signal through her deep brain stimulator, it goes, "Wah," and just feels like dipping it in warm water. And her brain goes, "Oh, you're fine," and stops hurting. Like she said, it's amazing. It's like, it's a miracle. There's other ones that people do with the mirror box. So if I'm missing my left hand, I put my right hand in front of a mirror, what shows up in the mirror?
The left hand.
My left hand. I can't feel it, but if I wiggle my left hand in front of the mirror, my occipital lobe goes to my parietal lobe and says, "Oh yeah, you're moving it like this." And all of a sudden the brain says, "Yeah, I can feel it." Yeah. And it's like, so the reason why this is so fascinating, especially to me, because I've been doing this for almost 30 years now, every time we learn something about the brain, it just gets more complicated. As opposed to trying to figure things out and make it easier, no. It's just like we learn a whole bunch that the Connectome project, that Sebastian Seiton guy that we watched last time, they discovered 96 new areas of the brain that we didn't know we had. 96 new parts that we didn't know we had that were connected, that we didn't know were connected because of his stupid mouse slices. Okay. So I kind of left out a big chunk. What's the big chunk that I left out? Wait for it. Adjusting. There you go. So the prefrontal cortex is right here. What's all this do? This is the frontal lobe. Good. That's the frontal lobe. The frontal lobe's main job produces behavior. So I've done this a few times in class, but so the frontal lobe is involved with behavior. Behavior, it's what you do. All your movements come from the frontal lobe. All your movements. Why would language be also in the frontal lobe? Say louder.
The way your mouth has to move.
Your mouth and tongue have to move in a certain sequence. We'll talk about this part down here. That allows you to speak fluently. But to know which words to say, which behaviors to produce, like if I go like this to my daughter, what does that mean? Come on, somebody watches Friends in here. Yeah. What does that mean? So one kid flipping off the other kid so the parents don't get mad. And there's one episode where the parents go to each other. Anyway, so you got to watch that more. Binge. Okay. So, if you speak more than one language fluently, you have two separate areas in your frontal lobe dedicated to one to each language. What about to yo-yoing? So, if I were to play with a yo-yo, how do I activate the motor muscles in order to get it to work? How do I do that? First of all, you spend a lot of time alone. Okay, so how do I get my muscles to move? What do we measure in her brain? Electrical activity. What happened when she blinked her eyes a bunch of times? What did the machine show? Spikes of electrical activity. So in order for us to move, this area right here, right next to where you feel, it's called the motor cortex. Every single neuron in here, I'm going to color it in this nice orange color because I really kind of like that nice burnt 70s orange color. Every neuron in this area is directly-ish connected to a muscle. So, where do you have the most muscles in your body? Oh, that was terrible. I missed. Let me fix that. Where do you have the most muscles in your body?
Face.
Your face. You have a huge area right here that is controlling your face. Technically, it's actually down here, but I just drew it up there, so you don't care. Well, I fix it now that I said that. Stupid. Okay. Why would your face be right here? What's right here? Language. Language is located right next to your facial muscles. So, how do you talk with an accent? The lady that cuts my hair, her name is Helen. She is Vietnamese. So when she speaks, she makes Vietnamese sounds but English words. My man Phu, actually retired now, so I can't make fun of Phu on campus because they say, "Hey, sup, Phu?" Phu Win was he was a guy that took all the pictures on campus, and his daughter was in my class. I'd never known that it was her, Michelle Win. Huh, weird. Put that together. Anyway, but he came to the United States when he was 26 from Vietnam. So when he's talking, he's ha, ha, ho, as he's talking. Why is he making those funny little sounds? He's actually using Vietnamese sounds to make English words. Vietnamese is a really pretty language. It flows. And the sounds that you make as you're saying the words change the meaning of the words. English, the words change. So for Phu, when he's trying to speak, he's ha, ha, he's making the little sounds as he's going. It's great. I do this all the time, and it's actually pretty offensive, but I go, "Hey, everybody!" And what's that from? See, how do you recognize Borat? It's really offensive, because I actually have a student from Kazakhstan, so it's really offensive to be Borat, or to be an American, because Borat's really offensive toward Americans, but whatever. You just, anytime somebody's doing something stupid, you want them to pull the mask off, and the guy's, "Hi, everybody!" Nah. You guys are tough, man. It's a tough crowd. Okay, so, but how do you make an accent? You change the way your muscles move to make the language sound differently. This is the whole motor cortex. Your hands have the second largest piece. Your hands. Your hands are very good at dexterous, tiny little muscle contractions to do some really cool things. I was just amazed that this morning I'm trying to put the electrodes in the machine. I'm able to hold a rubber band, manipulate this thing while stretching the rubber band out, put it on, slide the rubber band over so it doesn't slide off. That's a lot of things. That's a very complicated thing. And a robot's good at making movements. Not really. A robot can pick something up, move it over, and put it down exactly the same place 1,000,000 times. Humans can't. But a human can pick up something that is weighted funny and balance it, or it's really hard to make a robot play with a yo-yo. Trust me, the Japanese are trying. Okay? But why is it so hard to make it's my favorite trick right now. I just do that all the time. But why is it hard to make a robot do that?
Because of all the movement that you did to do that.
It's not the movement that's a problem. It's the feedback. The feedback's the problem. A robot could program the same pop and catch that I can do. A robot can program that. We can easily program that in a second. But is this on a fixed thing, or does it change every time? So how can I catch it? I adjust the catch to what I need it to do. I get cocky. Okay. But I can catch it because I can adjust based on the feedback that my body's coming in. Our muscles are not done in a fixed situation. We're not fixed in location. We're not rigid. We're flexible. That's why golfers make so much money. Anybody understand the physics of golf in here? If you swing a golf clubs are about 3 feet long. If I hold it at the end of my arm's length, a millimeter or two movement in my hands means that golf club can move 2 or 3 inches by the time it gets to the bottom. If you don't hit that golf club exactly at the right spot on the right part of the ball at the right time, the ball doesn't go where you want it to go. It's psychotically difficult. Can they make robots hit golf balls really well? Yes. Yeah, the TaylorMade. One of my buddies worked for TaylorMade. I know he won't give me free golf clubs. But he works on designing the club heads. He's an engineer, and they have a robot that swings the golf club exactly the same way every single time. And they put the robot in front of the golf. There's that stupid Budweiser commercial, Michelob Ultra commercial. The robot's hitting all the golf balls into the hole one after another, and then he's standing outside the bar not able to have a beer. Because the important part of golf is beer, evidently, based on the morals of that. Anyway. But the robots do everything perfectly, but they can't play golf as a real golf round. They can't manipulate. I've watched Mickelson do some crazy stuff with a golf club. Back when he was younger. Not so much anymore, but it's okay, Phil. So where are the very few muscles here? What systems have very little bit of muscles? Where do we have very little muscle control? Your feet are actually not too bad. People can learn to actually manipulate their feet. If people don't have hands, can use their feet to pick up stuff. But your leg and your trunk, these muscles in here, in fact, the ones that you use mostly for walking around, there's very few brains involved with those. How do you walk? We don't use muscle memory anymore. We use the word motor program. So I'm going to write this over here. I think I have room over there. So I love it when you say muscle memory, because that's the non-introduction to psych way of saying motor program. Okay, so your muscles don't really have memory, but your brain does. So what we do is there's a large portion, which again, for this class you don't need to know about it. It's called the premotor area. It stores motor programs. So like name a trick. Someone name a yo-yo trick. Someone knows a yo-yo trick.
Walk a dog.
Walk a dog. Okay. I'm going to get a cheaper yo-yo for that because it scratches up the yo-yo. Okay. But, so if you say walk the dog, I have a motor program on how to walk the dog. Okay? I don't know if there's a string that's knotted or not. Okay. So like, I can go all the way down here. Neighbor's dog. Oh, okay. Get it? Fucking gets in the leg. Bad dog? Runaway dog? Okay, can you throw it to me? It's back there somewhere. I don't know. Okay, so how come I can catch it? You guys are really tough. That was good. Okay. So how come I can catch it?
Yes,
My occipital lobe sees the information coming in. My frontal lobe, my prefrontal cortex, does math. It's called a Bayesian inference machine, if you really care. It does math. It calculates physics. It calculates trajectory. It predicts how many muscles I'm going to need in order to do what I'm going to do. When I used to coach Little League, it was a really big learning curve on how to catch balls thrown by children who don't know how to throw. Because which way is the ball going to go when a little kid gets ready to throw it at you? An infinite number of directions the ball can go. Fling! Straight back. Across the body. Straight this way. That's why we practice with tennis balls for the first couple of days of practice. Because Adam, man, he's going to be a professional pitcher at some point. He has the tennis and go, okay, throw it at me. Boom! It's just like, before you even get your hands up, it's like it's bouncing off your forehead. Because he's just got a rocket arm. And he killed probably 3 kids at first base. Because what's the kid at first base doing? Watching the runner. Adam gets the ball. Boom! We're like, no. Just watch the ball come in, just bruises all over the poor first baseman. Adam, make eye contact before you throw the ball. Got it. And you see him pitch the ball at him. Make sure the catcher's ready. At least he's wearing a mask. My son got one right in the side of the head. Ooh. Okay. He's never been good at math since. I'm kidding. Okay, so all of a sudden we start to see that everything on the surface goes to the prefrontal cortex. Everything on the surface goes to the prefrontal cortex. Everything. That's how you organize and plan and choose. So if you say name a trick, if I know the name of the trick, someone says, well, do the atomic squirrel. I'm like, my prefrontal cortex doesn't have a motor program to do an atomic squirrel. I don't know what an atomic squirrel is. Okay? And so as a result, my motor program's not there. If someone showed me how to do it through my occipital lobe, can I figure it out? Yeah, most things I can do with the yo-yo. The few things that I haven't quite figured out yet, but I'm working on it. I'm really not working on it. But if I see someone do something, I can probably learn it pretty quickly. Okay, so adjusting. Thank you. Okay. So, where's consciousness then? Where's your personality? Well, no, this is yourself. Some of you don't have a good sense of self, but still have a personality. High school kids, guess where this poor self does? Migrates all over the place. One day you're feeling good about yourself, you wake up in the morning, you got a zit on your nose, oh, the world hates me. And poor daughter last night didn't get set very much during the volleyball game. What's wrong? Why ain't I getting set very much? Because the really tall girl was blocking you, so they set the other side. Anyway, but why did she take it personally? She has a very annoying, strong sense of self. It's really irritating. It'd be much nicer if she didn't talk back quite so much. But in high school, a lot of yourself, when you're 16, 17 years old, a lot of yourself is based on the way the world reflects on you, not the way you reflect the world. So the world coming in, what you see, what you feel, and the way your body looks, that is the way that your self is defined. But as you get older, what starts defining yourself? Your prefrontal cortex starts sending signals back, feedback, to yourself. Hey, yeah, I might be a little bit squishy, but I'm working on it. Or I might have I might have some trouble at school, but I know what to do to help with my trouble at school. When you're 16 and you're having trouble in school, what's wrong with me? Why am I stupid? And where does that inner dialogue come from? Where does that narrative come from? Your temporal lobes. Your temporal lobes where you talk to yourself. We'll talk about a disorder called schizophrenia later in the semester. The person has too much activity in the temporal lobe. This part of the brain works too hard. So guess what they do? They hear things because their temporal lobe's too activated. So you hear something. Is there a classroom next door?
Yes.
How do you know? You can hear it occasionally. What if you're the only person who can hear it?
You're the only person that thinks that there's a-
So the only person who knows that there's a classroom next door. So everybody else doesn't know, so maybe you're special. Then we get to that stupid amygdala. Which lobe do you think the amygdala's in? It's right here. Your amygdala's inside the temporal lobe. What's the easiest way to trigger the amygdala? I'll give you a hint. Loud sounds. Boo! Ah! Boo! Ah! That's the best way to trigger the amygdala is loud sounds. It's located right underneath the auditory cortex. Maybe it's so you get pissed off when people talk to you. I don't know. Okay. So, we're going to go next class. I really suggest you go through those 2 brain chapters in the book. The brain chapters in the book are a little bit more in depth than we talk about in class. But we're going to do an activity next class. We're going to go through the middle part of the brain and the bottom. Then we're going to do an activity where you're going to become a big brain in class next week. Big brain.